Thank you, Dr. Magali. This basically here today, what I want to talk about is data acquisition and digital signal processing. It does not only apply to engineering. In many different fields, you have data acquisitions when you need to collect data. Sometimes manually, you put it into a form. Sometimes you use computers, right? With data acquisition systems, you use computers and collect a lot of data simultaneously. Now, digital signal processing, once we collect those data, all those data is called, each of those channels is called digital signals. Now, this digital signal processing, we can apply frequency analysis, for example, frequency analysis and spectrum analysis, a lot of different stuff to obtain whatever information we want from this signal. Otherwise, they're just raw data, right? So, I have my weapon. Okay, so first we'll go through data acquisition. For data acquisition, today we'll briefly talk about analog to digital conversion, which is very important, and we'll introduce you resolution of this kind of AD conversion. And then we'll talk about sampling frequency, which is very important when we're collecting data real time, when we're collecting real-time data. And aliasing is something related to sampling frequency that makes your signal to show up as in your computer as a different signal that is not the same as the original one. Okay, first I would like to introduce you guys some terminologies. What is analog signals? An analog signal basically means it's continuously valued signals. For example, light. Our eyes receive light, and that is one signal that goes into our brain. That's how we can see stuff, right? Now, light always continuously to us, right? So basically what it means for analog signals, for these continuous value signals, it means doesn't matter how small an interval you choose, there are always signals in between. There are always points in between. Now, digital signals on the other hand is discrete valued signal. So we take this signal with a certain step. Now, for the minimum, when you go to the minimum interval between two data points of the discrete signals, there will be no more points in between. If I want to draw the two signals, a very good example is an analog signal, you see a curve. Now for a digital signal, you see points. This represents two curves, same curve, but one is analog, the other is digital. So AD conversion. Why do we need AD conversion? Oh, by the way, AD conversion means analog to digital conversion. Why do we need analog to digital conversion? The reason we need this conversion is we wanted to use computers to collect our data. Now, all our computers right now is digital computers. They only know 1 and 0, right? They don't know other stuff. And they represent everything with 1 and 0. So everything in our computer is discretized. This way we need some mechanism to convert an analog signal into a digital signal. Otherwise, our computer cannot recognize it. In other words, our computer doesn't have the ability to recognize a continuous curve like this. It only has the ability to recognize each of these points on the curve. Okay? So that is why we need AD conversion. And AD conversion basically is a process to take a sample point, to take a fixed set of sample points from a continuous signal and make that a discretized digital signal. So how do we achieve an AD conversion? This, we first need to talk about binary numbers. In a computer, any number is represented by a combination of 1 and 0. For example, we use a 4-bit binary numbers. 4-bit binary numbers, we have all these combinations. All these combinations. We go from 0, 0, 0 all the way to 1, 1, 1. How many combinations we can have? We can count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6. 16. So we know that for a 4-bit binary number, we can represent a total of 16 different values. Okay? And that is exactly 2 to the power of n. 2 to the power of n, with n as the number of bits. Right? Think about 2 to the power of 4 is equal to 16. Now if we have 8-bit, then the number of values we can represent is going to be 2 to the power of 8. You can think about right now, we talk about 64-bit.
Right.
That's going to be a lot of different values we can represent.
How do you know? Just wondering what that was.
Yeah. Now, doesn't matter how many values we can represent, there is always a fixed number of values. We don't have infinite number of values in there. Right? So, let's take this 4-bit for example. If we want to use this 16 values to represent a range of voltage from 0 to 7.5 volts, then we have to take a step of 0.5 volts. We have to use a step of 0.5 volts, which means anything lower than 0.5 volts, our analog to digital converter will not be able to recognize because it's too low, right? The lowest voltage we can recognize is 0.5 volts. Now with a higher bit, this can be dramatically reduced, right? And how we do this analog to digital conversion? You can see a curve here. This is an example. A curve here with a fixed sampling rate, which means with a constant time step, right? With a constant time step. We have constant time steps. Here we have from T1, T2, T3, T4. 4 instantaneous time, right? 4 time instants. At T1, we say, hey, we take that value. This looks like is 2 point something, less than 2.5 volts. Less than 2.5 volts. Okay, so let's write it down. It's maybe 2.3 volts. Somewhere close to that. 2.3 volts. And then we go back to our table, we say, hey, 2.3 volts, we want to represent that with our binary numbers. 2.3 volts, no such a voltage. So what a analog to digital converter does is it's going to represent this with the closest value, with the closest voltage value. Okay, so with the 2.3 volt, we're actually getting close to 2.5, right? We're actually getting close to 2.5. Now here there are different algorithms. People design different algorithms. Sometimes they just simply run everything down. So doesn't matter it's close to what value, it just ram it down to 2.0. Sometimes people do a comparison and see which value is closer, and then of course the second one is better, right? So now we say, aha, this is close to 2.5. We use 2.5, like that. And our AD converter will then output a binary number of 0, 1, 0, 1. And our computer will read that binary number, and on the screen, it will translate that binary number into a voltage. Now, after it translates that into a voltage, you'll notice that it becomes 2.5 volts. It's not 2.3 volt anymore. So this is a resolution issue. So what is the resolution of an AD converter? The resolution of an AD converter is equal to the full-scale voltage divided by the number of values we can represent, right? So I'm looking for another weapon. So if we say our AD converter is taking an input of negative 5 volts to 5 volts, then our full-scale voltage is going to be 5, from negative 5 to 5. That's going to be 10 volts, right? Full-scale voltage. Now, if we're talking about number of bits as 2 to the power of 4 bits, still we talk about 4 bits. Now, this resolution Q is going to equal to the full-scale voltage divided by 2 to the power of 4, which is 16. So we have 10 volts divided by 16, some number. I don't want to do the calculation, but this is how you find out the resolution of your AD converter. Why is this important? Why is this important? Because with a higher number of bits, we are able to do a more precise measurement. Right? Now, usually with a higher number of bits, you can imagine there will be a higher price. Right? So here comes the quality and cost balance. Understanding the resolution issue, you will be able to balance very well between the quality of measurement and your cost. Now here is another example with an 8-bit converter. We can actually represent a total of 256 different values. So if we have our full-scale voltage, or voltage range from 0 to 5 volt, if our full-scale voltage is from 0 to 5 volt, which means full-scale voltage is 5 volts, then we use the smallest number to represent 0, the largest number to represent 5 volts. And the resolution is 5 volt divided by 2 to the power of 8, which is 19.5 millivolts. Okay, so that is the resolution issue. Another very important thing for data acquisition is sampling frequencies. The higher the sampling frequency is, the more samples we take within a specific time. Right? So basically the sampling frequency, or sometimes called sampling rate, is